Hi everyone, I'm Hao from Communication Science Institute. I'm working with Professor Willner, and the research project I'm working on is high capacity and spectrum efficient data transfer using orbital angular momentum.
Sorry, can you try that again? And can you put the microphone on your shirt so your jacket?
It's too low? What? Is it better now?
Yes.
Okay. Start in 5 seconds.
Yes.
Hi everyone, I'm Hao from Communication Science Institute. I'm working with the Professor Willner, and the project I'm working on is high capacity and spectrum efficient data transfer using orbital angular momentum. So first I would like to introduce the motivation. So in the telecommunication field, the problem we are facing is that the bandwidth demand is greater than the spectrum resource. So according to the expectation, greater than 60 terabit per second capacity will be needed by 2015. However, the available spectrum resource is only 15 terahertz. So the spectrum resource is really limited, and we need to improve the spectral efficiency of the data link. So here there are existing solutions, including squeezing the channel spacing or utilizing advanced modulation formats. And these two approaches are approaching their limit. And the method we are working on is space division multiplexing using orbital angular momentum. So here shows the concept of OAM. So normally we use the phase and the intensity to characterize a laser beam. And for a conventional Gaussian beam, it has a flat phase front and a Gaussian distributed intensity. Well, for an OAM beam, it has a helical phase front and a ring-shaped intensity. So for the generation and the detection, we can simply use a phase filter to convert a Gaussian beam into a OAM beam. And on the other hand, we can use an inverted phase filter to convert the OAM beam back into the Gaussian beam. So now the question is, why do we need OAM beam for communication? So the major reason is that different OAM beams are orthogonal to each other. So in other words, if we combine them together as spatially collocated beams, we can still separate them with each other and without losing any information. So the OAM beams provide us another degree of freedom to increase the capacity with the limited spectrum resource. So here is what we are working on. So we generate multiple different OAM modes together, and we multiplex them, and each of the OAM mode carry a different data streams. And then we propagate it in the free space. And at the receiver end, we can demultiplex them to acquire different data streams from each different mode. So here shows some experimental result. So we generate 4 different OAM modes: OAM plus 10, plus 12, plus 14, and plus 16. So we multiplex them together. We first achieved 4 different modes, and then we double the number of modes by using the plus and minus charge of OAM. And then we further double the number of modes by using the polarization division multiplexing. And finally, we use the concentric ring to double the number of modes again. So the inner ring and outer ring each carries 16 modes. So we achieve 32 modes multiplexing. So to summarize the result, we multiplexed 32 OAM modes on one wavelength, and each channel carries 80 gigabit per second signal. So the total capacity is 2.5 terabit per second. And the spectral efficiency we achieved is 95.7 bit per second per hertz, and this is the highest record in free space. So for the next step, we will continue to combine the OAM multiplexing with wavelength division multiplexing to further increase the spectral efficiency and the capacity of data link. Thank you.